Hi, greetings of the day. This is Abhishek Naluri. Welcome to my YouTube channel MSc Panda. And today we will discuss and solve a problem. The problem is to identify an unknown carbon material. For example, given an unknown sample, and if it is stated it's a carbon material, based on the carbon element. So how do you identify the material? So for this problem, you have a solution in the chemical sciences based on a characterization technique called Raman spectroscopy. So based on this technique, we can actually identify the unknown element, and this technique is widely used in most of the industries, both from electronics to chemical and pharma industries. And today this question is about carbon characterization. And for example, given a carbon material, and I would say there are many types of carbon materials, that is, the carbon can exist in different forms, and these are called allotropic forms of carbon. Just based on the orientation or the spatial 2D or 3D orientational changes of carbon, alignment of the carbon with respect to one other. So based on these arrangements of carbon in the system, the material itself and the properties of the material itself vary. Just for the sake of your understanding, you at the left you can see the different allotropes of carbon: the diamond, graphite, graphene, C60 and CNTs, carbon nanotubes. These are all considered to be allotropes, and the difference between all these materials, the building block it's the same, it's carbon, but the alignment and the orientations differ. So based on a different orientation, we term it or we name it accordingly, and the properties of the material itself, it varies drastically. So for example, assume the diamond, the carbon, it is as a carbon atom, as a ball, and the bond in which it is attached, the bond, the carbon, you have two atoms, carbon and carbon, and between it is you have some covalent bond between these two carbon atoms, and this is a bond. And in real term and practical scenarios, this bond is analogous to the spring system, and this ball is compared to that of a ball. Like, you assume a spring and a ball, you take a spring and suspend a ball at the bottom, then it is very similar to that of our system. So based on the vibrational modes at which it will actually the vibrations at which it will deflect or it will move, so that varies accordingly according to two systems. Just like the spring mass system, you have the stiffness of the spring, that is the bond strength, and the weight of the ball, that is the atomic weight of your element. So based on these two, we can actually identify the material, and this Raman spectroscopy deals with that. It actually identifies the vibrational frequency or the vibrational mode in which the atoms or the molecules in the chemical given material oscillates. So by identifying this vibrational frequency, every material has its own signature or fingerprint region of vibrational modes. So based on this, we can actually conclude we can actually figure it out, the material. So for example, let's deal with a problem given you can see, just like in the earlier case, I explained with a spring and a mass system, or a bond and the carbon system. So it depends on two factors. One is the stiffness, the bond strength of the bond strength, and second is the atomic weight. So as I said, this Raman spectroscopy is really helpful in order to find out the structure or morphology of a given material. But what if I say, if I take a material which have different structures or different similar orientations, for example diamond, silicon and germanium, all these three comes under the category and has a similar atomic arrangements, but here a variable, it's the atom, the atomic weight varies, and depending upon, as atomic weight varies, as I said, the frequency, the vibrational mode or the frequency, it varies according to the atomic weight and the bond strength. In this example, it is the bond strength remains the atomic weight varies from structure to structure, material to material, diamond, silicon and germanium. Since the atomic weight is increasing, you can see a shift towards your right. You can see a shift towards the right, because as a size increases, you can see that vibrational frequency at which a specific material has or possesses, that varies. So if you identify this peak position, that is the Raman shift, we term it as the Raman shift. It's the frequency at which it oscillates, and the y-axis, it's the intensity of oscillation or vibration. So based on this, we can actually figure it out what material it is. And the next problem arises when you take a material, the carbon material, in the same class of material, just like diamond and a graphite. How do you differentiate? Because it's carbon here and it's carbon here on the other side. So here it's interesting to know. In the left, you can see it's a tetrahedral arrangement of all the carbon atoms in a crystal structure, and the diamond peak, it's a single vibrational peak, because all the orientations and the bond strengths are equal throughout. So that's the reason you have a single vibrational frequency. But in the second case, the graphene or the graphite, you have a stack of two-dimensional layers of carbon arranged. So basically it's a three-dimensional view, and you have a stacks of 2D arrays of or layers of graphene. So in the second case, we can actually identify the material based on the bond strength. This scenario, it is related to bond strength, where the diamond, it's sp3 iodized or sp3 bonded. Sp3 bonded in the case of diamond, and sp2 bond in the case of graphite. So sp2 bond has it's stronger in nature. So just like your spring and a spring mass system, the stiffness or the bond strength, it's varying. Now in this second scenario, the bond strength varies, just like sp2 and sp3, the diamond and graphite. Now the bond strength varies. As the bond strength varies, the vibrational mode or the vibration frequency of the given system varies. And this system, you can see as the bond strength of sp2 is greater than that of sp3, that is in the case of diamond. So you can see a leftward shift or the down shift of the peak, that you can actually see it in the diamond, and that is called the G band. And that is identified, or it is considered to be the major peak identification for the graphite. So based on this technique, or based on this Raman spectroscopy technique, we can easily identify. And even in if you want to understand how sensitive is the Raman spectroscopy is, if you consider diamond and the nanocrystalline diamond and a nanocrystalline diamond, even the bond strengths are similar, even the orientations are similar, but even in this case, because of the finite effect gets into the picture, in the case of nano diamond, the peaks, the vibrational mode, or it will actually deviate. So this deviation, based on the deviation, we can actually sense it, what kind of material it is, what type of material it is. And Raman spectroscopy alone can't justify the type of material. You need to have some supporting characterization techniques as well, just to strengthen your identity of that specific material. And I hope this video is helpful to characterize your carbon materials, carbon forms in your labs. Thank you.